Great, thank you very much. Can you hear me okay? Is that coming through? Well, thanks to the Science Society for the very generous invitation to come back to Cambridge to give this seminar this evening. I spent 7 very happy years in Cambridge. It's always a delight to come back. And I spent many of those years going to Science Society talks, this particular society, also our college one. So it's a great pleasure, real great pleasure to be here to speak tonight. And thank you for coming along. I know you've all got lots of competing demands on your time, particularly at this time of year. So I'm a materials chemist, and our job as materials chemists is to make solids that do interesting and useful things. And in that context, the particular focus in my own group is really on 2 aspects of materials design. One is concept of flexibility, and the other is the concept of disorder. And at first sight, those might sound like quite different aspects of structures of solids. But what I'll hope to convince you with 1 or 2 examples tonight is that actually there are some common themes, and very often the kind of glue that links those 2 ideas together is really the role of geometry on the atomic scale in different sorts of materials. So I wanted to start tonight just with a couple of examples of what I mean by disorder, what I mean by flexibility, and then lead into a few examples of the work from our own group. I should say that when I say disorder, our focus is really on cases where disorder is far from random. And internally, we use the term correlated disorder to convey the idea that you can have disordered states with lots of patterns within them, but actually are far from random. So just to give some sort of intuition to disorder and its ubiquity in materials chemistry, I just wanted to start with this slide from one of my very favorite papers. Like all my favorite papers that had absolutely nothing to do with me. This is the work of Sharon Glotzer, who's a computational soft matter scientist at the University of Michigan. Perhaps you know her. She's very interested in using computer simulations to understand the role of geometry in determining the structures of assembly, sort of self-assembly of different systems. Okay, and in this paper, she's really addressing a very straightforward and fundamental question, which is to ask, if I take copies of polyhedra, all of the same kind, and ask the simple question of what happens if I bring copies of those polyhedra together to form a dense phase? What sorts of structures emerge? So that's a question that actually we've got good intuition about in certain cases. So for example, we all know that if we take copies of cubes and we pack them densely, cubes can fill space, and they can fill space in a periodic way, a bit like sugar cubes would pack into any container, for example. There might be some other results that are reasonably well known. It's well known, for example, that tetrahedra cannot fill space completely. If you take lots of copies of tetrahedra and you bring them as closely together as possible, you'll form a dense packing, but it won't fill space. And that dense packing is unusual in that it's actually characterized by quasi-periodicity. It's a quasi-crystalline arrangement that you get with tetrahedra. So it's a simple question to ask, but actually it has some pretty subtle answers. And in this study, really what Sharon did was just take all the sorts of polyhedra you might want to take, you know, the Platonic solids, the Archimedean solids, and just explore what actually emerges. And this little pie chart that you see is a summary of the different sorts of structures that come out of that simple problem. And there are a few things that this paper really spoke to me about at the time. And one was that in all of these different polyhedra, all of these different arrangements that you see here, actually the crystalline, the ordered arrangements, which are shown in the bottom in the sort of shades of green, they're the minority. And yet, you know, if I give first year lectures on the structures of solids, we pretend as though the world is made up of crystalline arrangements. Yet here it's the exception rather than the rule, even in this very simple case. The vast majority of packings of polyhedra are disordered in different ways. You'll know that plastic crystals are the cases where the positions of the polyhedra are ordered and periodic, but the orientations are not. And liquid crystals the other way around. The orientations are ordered, but the positions aren't. And then there's all of these sort of orange families on the left-hand side where we don't even have a language for the kind of disorder that's present. Yet they won't be random. They still pack in particular sorts of ways. Okay? And the other idea that I find very appealing in all of this is, of course, this propensity for order or disorder is somehow encoded in the shape of those objects. And that's appealing from a chemist's perspective because shape of molecules, for example, is something that we might have some control over. And this is when I say that geometry might play a particular role, for example, in disorder of different solids. That's the kind of nub of the idea that I wanted to get across, and we'll return to this in a few different examples later on. So disorder is one of these things that actually we don't necessarily have a particularly good intuition about. Our language is particularly poor, but I'll hope to show you that we can hope to control some aspects of it in particular ways by playing into these concepts of geometry. By contrast, flexibility is something that I think we do all have some human intuition for. If we say something's flexible or not, we've got a kind of sense for whether or not that's the case. I tend to think of objects like this. Here's a picture. These are called Hoberman spheres. Maybe you've seen them before. I don't want to admit how many hours of my life I've spent opening and closing this thing. When I had a cat, I used to put the cat, I didn't hurt the cat, but anyway, all those sorts of things. I don't know, if you haven't seen one before, they're kind of fun to play with, but I think most people would say this is something about this is a flexible structure. And what do we really mean by that? Well, it has a variety of different sorts of states. It can be closed or it can be open. And I can get from one to the other through some small perturbation, and maybe those are kind of generalizable ideas of what we might mean by flexibility. Obviously, these structures have some practical uses. These are kind of engineering structures, and these are used in, say, deployables. You know, used in space. You can open up a mirror and so on in space using these ideas. But of course, again, I think you'd easily accept that the properties of this are really just a function of the geometry. It wouldn't matter what I make this object out of, wood or plastic, what scale I make it. It will have essentially the same properties. Okay, so again, there's something about the geometry of the system that's playing into the flexibility. Perhaps one other idea just to convey is that very often I think there's a sense that flexible structures can have counterintuitive properties. Okay, so there's something that makes it enjoyable to do this with this object, and we can be a bit more specific about that. What's actually going on is that this object has what we call a negative Poisson ratio. So some of you will know that the Poisson ratio is just our way of saying if I have an object, a material, and I push on it in one direction, how does it respond in orthogonal directions? And most objects, like a beach ball or you or me, if we push in one direction, we get larger in the other directions. And that ratio is called the Poisson's ratio. And if it's the normal behavior, it's a positive Poisson ratio. So the thing that's actually weird about this object is that when we push on it in one direction, it gets smaller in orthogonal directions. And in fact, it gets smaller at the same rate that we're collapsing it. And that technically corresponds to a negative Poisson ratio. And it's a property of the geometry of this system. Okay? So I think I'm just trying to capture a few of the things that hopefully are really quite intuitive to us about flexible structures. And of course, if you can play these games on one length scale, you can play them on another. So for example, as chemists, what we might do is actually just say, well, how do we devise architectures on the atomic scale that make use of these sort of flexible connectivities? And there's lots of different things you could do. I'm not going to go through many examples. This is just an example from some of the relatively early work in the group about a decade ago. This is a property called negative compressibility, and let me explain what's going on here. We've got a solid that instead of just squeezing in one direction, we're going to squeeze it simultaneously in every direction. Technically, we're applying hydrostatic pressure. And of course, that's the pressure that we would feel if we went into water, for example, at some depth. Now, thermodynamics tells us how a material has to respond under that hydrostatic pressure. A system has to reduce its volume. That's what comes out of the thermodynamics. But there's nothing to say that you have to reduce your volume by shrinking in every direction. And this is where this idea of negative compressibility comes from, because what these materials do is that they use a kind of flexible mode such that when they reduce their volume, they do so by getting longer in particular directions. Okay, that's this negative compressibility idea. So here, this is just a fragment of the structure. It's got some spirals in it and so on. There are two measures of the dimensions of this system, and one of these is shown in red and one is shown in blue. We can use crystallographic experiments to monitor the size of the crystal as we apply pressure. And the plot you see here just gives us those two dimensions as a function of pressure. So it's collapsing along that red direction. That's this plot that comes down. But it's actually expanding in this vertical direction as you apply pressure. And it expands by about 10%, actually, as you apply pressure here, which is not insignificant. And it turns out you can use these negative compressibility materials as things like pressure sensors. And the other sort of world where people are kind of interested in them is sort of as artificial muscles, and that's the meaning of the pictures. You might not be surprised to know this is not a picture of me, but this is in all of us. I think I've got a muscle somewhere. The way the muscles work, of course, is we apply a voltage to the cell and it contracts. But in squid and octopus, for example, there's a completely different mechanism for muscular motion. And in those cases, what they have are sort of spirals of tendons. And instead of applying pressure from the outside, like we've done in the experiment, they actually inject fluid within those structures. So it's like a negative pressure. And as they apply that negative pressure, the helical array shortens. So it's the opposite of what we see here. We apply pressure and it gets longer. A squid or an octopus applies internal pressure and it gets shorter. So that's the way they actually carry out muscular motion, for example. Okay. This idea of negative compressibility, it's not actually that counterintuitive. Something like a wine rack shows essentially the same behavior. If we think about the volume that's occupied by that wine rack, and I say I'm going to reduce the volume of it, I'm going to pack it up. Well, we know what you're going to do, and as you do that, I'm not very good at holding it steady, but I think you'll be happy with the idea that it's actually getting slightly longer in the vertical direction as we do that. And it's exactly the same sort of approach as what's going on in this particular material. Okay, so the flexibility is associated with that particular property, and we're not by no means the only group to have a look at all these things. You can play around with, use the fact that basically building these architectures is a bit like Lego, so you can design lots of different structures that show these sorts of properties. This is an example from the group of Gérard Ferré, again from some time ago, that I thought I'd just show very quickly. It makes use of a particular kind of chemistry called metal organic framework chemistry, or MOF chemistry. And I thought I'd just show it in case you haven't seen MOF chemistry. But if you haven't, the chemistry is really very straightforward. You've got a metal bit and you've got an organic bit, and you connect the metals to each other by the organic bit to form a framework. So the clue's all in the name, okay? And here the metal bits are in the little green polyhedra that you see. Here are the organic bits connecting them. And these are fragments of a structure that would repeat. And these are two different views of that structure. So when you look down the top, this particular structure has has big holes in it. And in fact, you can prepare it in one of two ways, and it can switch between these, where the diameter of those holes changes in response to whether or not you've got some molecules for the system to take up, some guest molecules to go in it, okay? And it goes from one to the other by effectively hinging. I often think this system's a bit like my colleagues in the department at Oxford, where if you give it ethanol, it opens up, and that's exactly the same as same. Okay, so this one, you give it ethanol, it opens like this, you take the ethanol out, and it closes up like that. It's called Mil-88, for example. So two different states, that's a kind of flexibility. And there are lots of games you can play. We've been talking about wine racks. In the field, there are lots of different geometric motifs you might use. You can imagine things like ratchets and springs and so on. So there's a whole field of playing around with different versions of those, and I won't go into all of those today. Just thought I'd make a link, though, of course, if these things work on the atomic scale in artificial materials, of course, it's no surprise that nature uses exactly these same ideas. And the one that, comes to mind is that of allosteric responses of proteins, for example. So in hemoglobin, you'll know it's got 4 subunits. When one of them binds an oxygen molecule, that binding event causes a relatively large structural change that then changes the affinity for oxygen at the other sites. And that's what's responsible for the particular uptake curve of oxygen in our blood that turns out to be very important. And if you think about it, what did we say was something flexible? A small perturbation gives rise to a relatively large change of structure. Sort of conceptually, these things are sort of related. It can be in one of two states, for example. Okay. So you might say, actually, I can see these similarities of flexibility mechanisms in different sorts of systems. What different kinds of flexibility could there be? And there's no right answer to this. I'm just putting up some different ideas here. So one is we've got some systems that you might say have a kind of discrete flexibility, by which I mean that there's, you've got an open state and a closed state, for example. And the idea of those systems being flexible is that actually the energies of those two states are relatively similar, such that small perturbations to the system, the binding of an ethanol molecule or whatever, can actually tip the system in favor of one versus the other, for example. And that might be the kind of thing that we saw in those metal-organic frameworks. you could say that maybe some systems have a sort of continuous degree of flexibility. That's a bit like what we've got here. The system has lots of different possible volumes, and it can explore each of those relatively straightforwardly. You might characterize a particular state, now not in terms of whether it's closed or open, but rather the internal angle of something, for example, and that behaves like a continuous parameter for that system. So you might go from something that has a discrete degree of freedom to something that has a continuous degree of freedom. An example on the right-hand side is something I've just called complex, for want of a better word. But this is where the degrees of freedom are not so easily identified as individual components. So this is a sort of flexibility you might get in something like proteins, where you go from one state to another, not by changing just a single angle, but through some very complex cooperative motion. This particular example is taken from a very nice paper from Matt Rosinski's group, where he was looking at metal-organic framework architectures, but where he'd used polypeptides to link the metals together. And he was able to show that when you put different guest molecules in these systems, they actually underwent a kind of collective reorganization, a bit like you would get in proteins, like we saw with heme. And now these different states that you end up with, and he's given them different labels here, they're associated with different combinations of torsion angles of the framework, for example. So I'm just putting that here as a kind of more complex system. But the reason I'm doing this is I want to make the kind of conceptual link between these flexible systems and disordered systems. Because in each of these cases, what we have is a configurational landscape of states of similar energies that we can perhaps get from one to another using some perturbation to the system. And I think that's where the kind of, on the sort of simplest level, the link to disorder comes from. So let me show you an example of a disordered system with non-random disorder. And let's explore the idea of the mapping to flexibility. The particular example I'm using here is it's a statistical mechanical model known as the Ising triangular antiferromagnet. And let me just take a few moments to talk through it in case it's not obvious to you. There's a lot on this slide. So there's three ingredients in this model. And the first bit, the thing that's called Ising, is the fact that this model's made up of states. It can either be white or black, one or the other, +1, -1, it can be a spin up, spin down, it doesn't matter. The fact it's Ising, it's like a discrete degree of freedom. The triangular component comes from the geometry, how those degrees of freedom are arranged. So in this case, for example, all of these little hexagonal tiles are arranged such that they have 6 neighbors. They form little triplets of neighboring sites, okay? And that's the triangular component. And the final bit is antiferromagnet, which is making it sound like it's magnetic, but it doesn't have to be magnetic. It's just the idea that the energy of the system, for whatever reason, is minimized by having neighboring sites in opposite states. So if one site is black, the energy of that site will be minimized by having all of its neighbors as white, for example. And this little model, where you have Ising degrees of freedom on a triangular lattice, trying to have neighboring sites in opposite states, gives rise to a very sort of famous model of disorder. And the reason it does is because there's no way of satisfying the rules. It's what we call geometrically frustrated. And that's easy to see because for any individual triplet of states on one of these triangular plaquettes, we've got 3 states at the vertices, and we can't make all 3 pairs of opposite state. The best we can do is to have, say, 2 black and 1 white, or 2 white and 1 black. The worst case scenario would be to have all 3 of the same color, for example. Okay. So in the ground state of this model, the energy minimum for the system, you have an arrangement where every triplet satisfies that rule of 2 black, 1 white, 2 white, 1 black. This one is close to the minimum, but there's still some triplets of all white or all black, so this would be close to the minimum. And it was shown back in the 1950s by Vanier that there's no unique way of doing this. There's a whole family of equivalent ways of satisfying those rules. And he was very specific about what he means by a family. He actually calculated the entropy of that ground state, effectively counting the number of ways of doing that. And here's the answer. It's not at all obvious, but the key bit is that the number of different possible states with the same energy grows with the system size. Now, that's something that's conceptually very different to what we were talking about in terms of configurational degeneracy of flexible systems, because here there's 1 degree of freedom, and it doesn't matter how big or small I make this object, it will always have 1 degree of freedom. What this is saying is that the family of states with the same energy will actually double if I double the size of the state of the system, for example. There are more degrees of freedom the bigger the system you make, and that's quite sort of extraordinary. And in fact, it allows you to actually store information in these states. Now, the point I'm making on the right-hand side here is to get home how delicate this particular situation is with respect to those three ingredients, the Ising bit, the triangular bit, and the antiferromagnet bit. Because if I change any of those, I come out of this disordered arrangement and I go into ordered ones. So the example at the top is if instead of having my sites only black or white, imagine I had a vector that could point in some direction, okay? And in this case, this might be called an XY vector. Then it turns out that the system will order. There's a unique way of satisfying the rules, and it's shown by this arrangement you see at the top, where each triplet has vectors at 120 degrees to each other. If I had, instead of changing the degree of freedom, if I'd changed the geometry of the lattice, so I'm not arranging them on triangles, I'm arranging them on squares, then again the system orders. It just becomes a trivial case of checkerboard ordering. You know, you can make sure that every one of these is the opposite state to its four neighbors. And likewise, if I had changed the interactions, instead of neighboring sites trying to be in the opposite state, if they're trying to be in the same state, then there's a trivial solution where everything is the same state, and that would be the case that you see down the bottom here. So those three ingredients, it's this sort of balance between them that is giving rise to disorder in this case. And can you see that there's a geometric component there as well? So I'd say there's a very loose geometric sort of mapping to what Sharon was finding with her polyhedra. Certain polyhedra are predisposed to order, certain are predisposed to disorder. And in the same way for these models of disordered systems, particular combinations will favor order or disorder. So I won't go to this in any detail today, but one of the approaches we would take in the group is to think about what are the different sorts of combinations, what different degrees of freedom can we have in materials, what different geometries of lattices do we have, what sorts of interactions can you have, and then you can explore lots of different combinations of these. And we draw on a lot of the theory from statistical mechanics in order to explore those. Okay. So let me just give you a sort of concrete chemical example of doing exactly this. And this is a system known as a benzene trisamide. I'll show you some experimental data for this in just a moment. So chemically, these are just basically planar molecules. And like most planar molecules, they stack on top of each other to form a column. But the edge of the molecule is decorated by amides. And those amides will hydrogen bond from one to the next. The hydrogen bonds form a kind of helix around the outside. But all of those hydrogen bonds, they will point in one direction. And that means that this column, as it self-assembles, has a positive end and a negative end, a dipole associated with it. Okay? So when these self-assemble in the solid state, these columns form with their dipoles, and then the columns come together to pack. And how do columns pack? We know how they pack. Think of dry spaghetti as you pack it. That's how this thing packs. So each one of these columns, they all get aligned, and each column is going to have 6 neighbors. The columns pack on a triangular lattice. That's a solution to that, okay? So we've got our degree of freedom from the fact that these hydrogen bonds could either go up or down, plus or minus, black or white. We get the lattice from the fact that sort of columnar objects pack like dense spaghetti, like hard spaghetti. And the final bit is the interactions. And of course, you know how dipoles interact. Neighboring dipoles want to point in opposite directions. Okay, so the interaction is also encoded in the geometry of the system. And so this system adopts a state that is related to that Ising triangular antiferromagnet. And I'll show you the experimental evidence for this in just a moment. Okay, so that's the kind of ingredients you might use to realize one of these sorts of things. It does beg the question, of course, if you're going to make these disordered systems, how do you know that you've made them? And what's the evidence? I've just shown you a bunch of cartoons, and you've very politely nodded along and accepted that this thing is going to form the Ising triangular antiferromagnet. But how do we know? And experimentally, our key technique for characterizing these disordered systems is something called diffuse scattering. And this is just a brief slide to just introduce it in kind of quite naughty terms. It's effectively a form of crystallography. It's the same as a conventional crystallographic experiment. So you and I know that if I've got an ordered crystal, sodium chloride, and I fire a beam of radiation X-rays at it, I will see a diffraction pattern, which is effectively an interference pattern from the scattering events that occur. And if it's a crystal, then that diffraction pattern will contain a regularly arranged set of spots. And 20th century crystallography taught us how to interpret these patterns. The arrangement of the spots tells us about the size of the unit cell, and the intensities of the spots tells us about the positions of the atoms in the unit cell. Okay. So we can solve all of this and work out the structure. Now, if I took something that was very disordered, like a liquid or a glass, and I carry out the same experiment, the atoms don't know that they're not in a crystal. They still scatter the radiation. I still get an interference pattern. It just looks very different. And it would look something like this on the right-hand side. Now, if the structure were truly random, you can show that this interference pattern would just be one single structureless blob, most intense in the middle and die off. So here, it's what we'd call diffuse features, because these are very broad relative to these original spots. They're kind of concentric rings, but there's some modulation in it. And the fact that there's even that modulation is telling us that in a liquid or a glass, the structure is not random. So if it were window glass, for example, there'd be information about the silicon-oxygen bond length, which is well defined in silica glass, and that information is contained within it. But this diffuse scattering is very hard to interpret directly, and you can't use kind of conventional crystallographic approaches to do so. But very many of the systems that we would study in our own research group, and the kind of disordered systems that I'll show you today, kind of live between these two extremes. There's some aspect of the structure that is still periodic and crystal-like, and as a consequence, the diffraction patterns still contain a regularly arranged set of spots. But superimposed on top of that is some diffuse scattering, okay, this sort of continuous scattering. It's a cousin of what you would see for a liquid or a glass. And the presence of that in your diffraction pattern tells you your system is disordered. And in the same way that the fact that this is not a featureless blob told you that there's some pattern in the structure of a glass, so is it the case that this continuous scattering and its shape tells us that the disorder that's present is not random, that there are patterns within it. Okay? So we sort of specialize in the measurement and the interpretation of these patterns. And I'd say there's a lot of good 21st century structural problems associated with exactly that. Just to show you, so you've got a sense for the experiments, you can measure these in lots of different ways. You can go to synchrotrons or neutron sources to do it. You can use electrons, X-rays if you want. We do quite a lot of work using just a conventional single crystal diffractometer in our lab at Oxford. We've just got a very nice detector that's good at picking up this diffuse scattering, which can be extremely weak. And let me just give you a little bit of a feeling for it. This is, we're about to see a little movie. Ariana, the postdoc, was taking a picture of it, sort of Blair Witch Project. So it's going to be a little bit shaky when we do it. But in case you haven't done one of these experiments before, you grow a crystal in the lab, you mount it on a little pin, and then you're firing X-rays at it, and you're looking at that interference pattern in your detector. And it's a bit of a slice through that diffraction pattern. So in this still, you can see a few of those Bragg reflections. The space is a bit warped in this geometry, so it looks a bit warped. But these are the Bragg reflections, and that's what you would normally analyze. You just keep turning your crystal, and you'd measure different bits of this. But the diffuse scattering is very weak, and we measure it by, instead of turning the crystal very quickly, we just stay in that one spot, and we just keep measuring it. And here, Ariana's just taking a little movie of it. And can you see in the background, just very slowly, sort of coming out of nowhere, is this diffuse scattering that sits there, just slowly starts emerging. Okay, and that's the signature of disorder in these materials. And we'll do that. It might take us a day in the end to measure a whole pattern for one of these crystals. But then it takes us about 3 years to work out what the disorder is or something like that. So experiment is still quite short. But can you see that? I don't know how well this is coming out. Can you see that sort of emerging from the background there? Very good. Okay, great. So for example, when I said that those benzene trisamides correspond to the Ising triangular antiferromagnet, the way we know is because the experimental diffraction pattern has diffuse scattering that we can show is associated with that. So if you have this sort of model, what you end up with is continuous scattering that sits on these sort of connected hexagons. And there's a bit of theory that explains that. Here's one of the bits of the diffraction pattern for that benzene trisamide, and you can see all of these connected rings like that continuous scattering. It's characteristic of this disordered state. And the reason that I'm showing this GAG protein fragment here, this is a beautiful work of Richard Welbury, this is a chemically entirely different system. It's a protein, that when it crystallizes, the protein can be in one of two orientations, and neighboring fragments are pointing in the opposite direction. They're sat on a triangular lattice. So even though the chemistry is entirely different, because the underlying physics is the same, the model of disorder is the same, and the underlying scattering pattern is the same as well. The fact that the intensities are in slightly different places is just capturing the idea that one of them is a protein and one of them is a benzene trisamide, and it's got that information within it, okay? So this is where you see these sort of geometric mappings between quite different sorts of materials. And for that reason, in our own group, we actually intentionally study lots of different sorts of materials. We're not tied to metal-organic frameworks or proteins or ferroelectrics or whatever. We're intentionally looking across very different systems. And this is just a snapshot of some of the different sorts of materials that we've been looking at in the last few years. But don't worry, I'm not going to bore you with all of these stories today. I'm really just going to focus on one story that I wanted to share, in part because it's a recent result, and in part because I think it's a good example that ties together some of the ideas of disorder with some of the ideas of flexibility, and that involves these so-called Truchet metal-organic frameworks, and that's the last story I need to tell you today, if that's okay. Now, so the chemistry is going to be metal-organic framework chemistry, and we've already touched on that. But maybe you haven't come across Truchet before, and if you haven't, let me just tell you a little bit about a Truchet tiling. They're named after this chap, Sébastien Truchet, and he was a monk in France in the 18th century. He was actually the chief scientific advisor to Louis XIV. And he's a bit of a polymath. If you look him up, every time I go on Google and have a look, there's always something new. You find out lots of really interesting things. I reckon he's got a bit of a knack for finding things that sound really obvious, but at the end of the day have something quite profound hidden in them. So, for example, you know when we type a document, we choose a font and then we go like times 12 point or whatever. So he invented the point. He didn't invent 12, but when you think about it, okay, it sounds like a really obvious thing to invent. How can you invent the point? And the story apparently goes that Louis XIV, in his court, had all of these court circulars that were going around, and everyone's using fancy writing to do them all. And he decided he wanted to have a uniform way of these court circulars being produced. So he tasked his chief scientific advisor with saying, can you work out a way that everyone writes the same? You know, I want an official way of writing these documents. So what Truchet did is he took his favorite version of the letters for each one, and then to standardize it, he put a grid on top of it, of the letter, and worked out which bits of the grid were covered and which bits weren't. And effectively, he's digitizing it. And then that becomes the code for how to write the letter. And of course, as soon as you do that, you have to decide how fine your grid's going to be, and you invent the point. And ever since then, we've had the point. That's the guy who came up with it, okay? So the other thing that he did that I think is equally sort of obvious, but I think also has just a nub of something really interesting in it, is what gives rise to these so-called Truchet tilings. So he's going around France, and he comes across a chateau in Orléans. And as he's wandering around the chateau, he realizes that they've got all these different patterns on the walls, all generated just using this one tile. A square that's painted differently either side of the diagonal. And he realized, of course, that that decoration lowers the symmetry of the tiles such that all of a sudden it looks different in each of its four orientations. Again, a really obvious thing. And that different sort of orientations mean you can produce lots of different patterns. They needn't be ordered. In the palace they were ordered, but they needn't be. But here's the conceptual bit, because he says, actually, the fact that you can distinguish them means that you could associate a different number with each one of these. You could say 1, 2, 3, 4. It's storing information in base 4. And all of a sudden, these patterns that you see here become a way of storing information, actually quite densely. So he's gone from inventing the point to inventing what's almost sort of the QR code, you know, an early version of the barcode. Again, something quite simple, but I think there's something profound about it, okay? So actually, the visual information community, the people that do invent things like barcodes and QR codes, latched onto this idea, particularly in the 1980s, and they've generalized the concept of Truchet tiling. So Truchet tiling is where you take a high symmetry tile, could be a square, could be something else, and you do something, you decorate it to lower the symmetry of the tile, okay? That's as simple as that, and there's lots of different examples of them. Let me show you a little movie of some of them. This is a little animation of a Truchet tiling. This one, again, is based on squares, but it has a decoration now. There's two different orientations. And can you see how it's a great sort of example of the coexistence of order and disorder? Because the arrangement of the tiles is still periodic and ordered. The underlying tiling is based on something very highly symmetric. But by lowering the symmetry of the tile through the decoration, you access something that is not necessarily periodic, could be disordered, okay? And you might think of each one of these states as encoding some information. The other idea that it might come back to when we were talking about flexibility is having lots of different configurations of similar energies. If this is some form of connectivity, you could imagine this is a system that has lots of different states of equivalent energies as well. So this is sort of configurationally flexible in some way. And when you see this as a chemist, you go, well, I don't know, some people might go, that's very nice, Andrew, but it doesn't look very useful. Other people might go, oh, that looks kind of cool. How do I make one? What do I do? How do I synthesize one of these on the atomic scale? Okay. So I want to show you how we think we've made one of these on the atomic scale and some of the properties of these Truchet tile systems. But before I do, we need to just sort of check how we would know if I did make one. How would we know that I'd actually make it? How am I going to convince you that that's the case? Okay. And I'm showing that here with a couple of examples, just to show you some different sort of Truchet tiles. So here again, squares decorated. This one's got some hexagons and some triangles. You don't have to decorate all of them. You can have different ones in it. There's lots of games. There's an infinite number of different Truchet tilings you could generate. But if you take one like this one on the left, and you say I did this on the atomic scale, our way of characterizing it would be to use crystallography, to use a diffraction experiment. And the diffraction pattern for something like this looks like what you see on the right. It's the sort of diffraction pattern that we're used to interpreting in this world of disorder. It has a set of Bragg reflections, these repeating spots, that capture the underlying periodicity of the tiling. So the fact that this is made from square tiles of a particular size, that information is contained within these spots. And if you use the intensities of those spots in conventional crystallography, mathematically it has the equivalent, it's equivalent to saying, I know the geometry of the average tile as in the superposition of all of the possible orientations of the tile. So you'd see a very highly symmetric arrangement in this average structure with partial occupancies of your different strands, for example. So that's sort of configurational average. The information about the actual Truchet tiling, that's buried in the diffuse scattering, and you would have to analyze or reproduce that in order to get there, okay? So how have we gone about making these things? We're using this meta-organic framework chemistry, and I'm going to show you some ordered meta-organic framework chemistry to start with, just to show how we're going to take a structure, a chemical structure, and think of it in terms of a tiling. And the problem is we're now dealing with three-dimensional structures, so our tiles are not squares, they're blocks, okay? So here, this is the kind of canonical meta-organic framework. It's something called MOF5. And let me quickly summarize its chemistry. The metal bit is this tetrahedral cluster of zinc atoms. And those clusters have sort of chemical connectivity that means that they will bind 6 carboxylates in an octahedral arrangement. So we link them together by taking a dicarboxylic acid, in this case 1,4-benzene dicarboxylate, and that's this panel here. So it can fit 6 of these around each of these clusters in an octahedral arrangement, and each one of these will connect 2 clusters. So when you do that together chemically, you produce this very simple cubic arrangement of clusters and linkers. So that's the ordered arrangement. How do I think about this in terms of a tiling? Well, what I do is technically I just split this into what's called the Voronoi tessellation. And all Voronoi does is say, for each point in space, you work out, are you nearest a node or nearest a linker? And the volume of space that is nearest a given node or a given linker will form a three-dimensional block. And by definition, because every point in space is nearer one or the other, those blocks will fill space. It's a space-filling arrangement by design. So here, for example, there's 2 kinds of blocks. There's the regions of space closest to a node, and that little polyhedron, that little block, is a cube. And in the regions of space that are actually closest to a linker, closer to a linker than anything else, that region of space is this truncated square bipyramid. And here what we're doing is we're decorating those blocks from the underlying chemical connectivity. Okay? So here, this little octahedron in the middle is because that we're going to have octahedral connections. And notice that this connectivity, here's the linker that bridges 2, that connectivity doesn't break the symmetry. So when I take copies of those blocks and I put them together, there's a single way of doing it. And the connectivity that you produce of these connected little octahedra, that's the same connectivity as the underlying meta-organic framework. Okay, so there's no disorder. The propensity for order is encoded in the blocks. So what have we done chemically? Well, we've done the very simplest thing, and this is a kind of concept that we would use in lots of different areas. We start from a high symmetry thing, and then we lower the symmetry of one of the components. Okay? So in this case, we're using exactly the same cluster, but we just use a bent version of the linker instead of a straight one. Chemically, they're still going to do exactly the same thing. Clusters still want to have 6 carboxylates around them. Each linker wants to connect 2 clusters, okay? But we've lowered the symmetry of the components. And when you grow the crystals of this material, what you find is some diffuse scattering. I'll show you in a moment. Some Bragg reflections. And when you solve the structure from the Bragg reflections, you get a very high symmetry structure like this, with clusters on a face center cubic lattice. And the linkers, we know chemically we've put them in a cis, but it looks as though we've got sort of triplets of them, for example. And they've all got partial occupancies. Now, what's going on? Well, each one of these nodes, a face center cubic lattice, each node site here has 12 neighbors at the same distance. But chemically, it can only be connected to 6. So it has to choose 6 of the 12. And when you do that on this lattice, you have to break the symmetry. There's no way of doing that and keeping the symmetry at the site. So when we do our Voronoi tessellation, the region of space associated with these clusters, when we draw in the connectivity, we have to show that symmetry breaking, the fact that you choose 6 out of the 12 edges, as it were, okay? There are, in fact, 24 equivalent ways of doing that for those who are interested. And likewise, on the sites where the linkers are positioned, well, actually, in this structure, the linker doesn't have the threefold. Here's what that polyhedron looks like. It's a trigonal bipyramid, so it has threefold symmetry, but the linker doesn't have that. So when it's sat on the site, the connectivity breaks that symmetry. And in fact, to get the stoichiometry right, you have to have some sites that are actually entirely vacant. So now when you take these blocks and you put them together and make everything match up, these are the Truchet tiles. There's an infinite number of ways of having these all match up, and every time you do it, you'll get something different, okay? So just to take these tilings and just show how they map onto the chemistry, for every one of these arrangements that you might generate, you can generate a corresponding arrangement of clusters and linkers with sensible chemical connectivity, okay? As we go from one to the other, here's this green sort of path as you go from one to the next. But if you do this in a different way, you'll get a different connectivity again, okay? So this is how we actually prove what's going on in the real material. We make lots of different models. We use density functional theory to relax all of the coordinates, and then we calculate from that ensemble the diffuse scattering. And we compare what we get from our calculations of the diffuse scattering with the experiment, and this kind of match is symptomatic of the fact that we've got the structure right, okay? So this is a very weird material. It's based on a periodic arrangement of clusters, like a Truchet tiling. It's based on something periodic. So here the arrangement of these red spheres, the clusters, is actually periodic. They've all got the same local connectivity, but they connect up to form a network that never repeats. And the channels of these systems are entirely disordered, but in a non-random way. And again, every time we grow a crystal, it's got a different connectivity. So you might think of these things as kind of storing information within each individual crystal. And all I wanted to do to finish things today in the last couple of minutes was just to show you the implications of this for the flexibility of the material. It's kind of just to bring it home to flexibility. So we've just done the obvious experiment with it, which is that you take that system and you squeeze it like we squeezed our things before. And when we had something that was periodic and like a wine rack, we squeeze it and it gets longer. This thing is disordered. It has the symmetry of a cube. So when you squeeze it, it has no option but to get shorter in every direction. But the thing that turns out to be very weird about it, and it doesn't sound very exciting to start with, is that when you squeeze it, you can keep squeezing it. It just keeps getting smaller and smaller. And in fact, you can take it to the limit of the experiments that you do these things. This thing in gigapascals, it turns out there are technical reasons why for these MOFs you can't go much higher than a couple of gigapascals. So TrueMOF 1 just keeps reducing its volume, whereas every other ordered metal-organic framework collapses by the time you get to those pressures. So that MOF 5 that I showed you, the ordered version with the same chemistry, the same connectivity, actually dies by a third of a GPa all the way down here. So for some reason, having a disordered system makes it more mechanically robust. And we've understood where that comes from by building some very simple elastic models based on the unusual connectivity of this particular system. Okay? So here what I'm showing you is a slice through a three-dimensional model. Each one of these little circles is meant to represent a node of the structure, and every line is just a connection you'd have through the linkers. So we can take this and we can put springs on all of these sorts of lines and see how the system behaves when we apply pressure. And what you notice is that actually, as you squeeze the system, you activate all sorts of different motifs. You've got bits that are behaving like wine racks, you've got bits that are behaving like little ratchets, all of the things that we're used to using in our conventional ordered materials all live within here. But the key bit is that it doesn't do the same thing in all the same place. So it doesn't all collapse in the same direction. One bit's going one way, another bit goes another way. And that's what actually stops it from undergoing any general collapse. And we can check that against experiment. So really, the way we're thinking about this is that this is actually very similar to the way we might strengthen things using disorder just in human experience. So for example, if you're building a dry stone wall where you don't have any mortar, you need something that's structurally robust. You don't use stones of the same size. Because if you do, an entire row will fall off, for example. The whole idea with these things is to use stones of different sizes so that it frustrates the collapse of the system. Nature uses exactly the same idea to strengthen termite nests, for example. Has an irregularity of support network in those things to make them as robust as possible for the given amount of matter. So we think it's exactly the same idea occurring within the system. Okay. So I think that's all I really wanted to share with you today. Hopefully I've conveyed the idea that very simple geometric ideas play into both the concepts of flexibility in materials and also the concepts of disorder. And though I haven't been super rigorous about it, there's often some concrete mappings between the way we think about one and think about the other in these different sorts of systems. And ultimately, if our job is to make materials that do interesting and useful things, I think personally that disorder is a really interesting approach that's pretty much entirely underexplored. That gives us a sort of insight to lots of different sorts of systems. So let me finish there. I'll just finish by thanking my very nice research group. We have a tiny research group at Oxford, but very, very wonderful people, interests across the sort of chemistry, physics, materials, maths domains. I'm very grateful to them. My funders, particularly the European Research Council, which has done a lot of our funding. And let me thank you all for your attention this evening.